Good morning. It's time again to look at images, and this time we're going into a bit more advanced techniques for the segmentation. Until now, we have learned how the histogram can find the threshold in the histogram, but we also know that it's not always so easy to segment images only using a histogram. And today we're going into looking into methods. First of all, how to find the threshold, but then also looking into more advanced techniques from the machine learning. And this one didn't work. So now it works. So we have, again, the motivation. We have many samples. We have difficult samples with features that are barely visible or hides within other structures, etc. We have also looked a little bit into training and learning. We are going to look at also automated methods for finding the threshold, and one is then going a little bit further using a hysteresis for the threshold. And then first looking on unsupervised methods for the segmentation. K means clustering, superpixels. And the other one comes in the second part, which is the supervised segmentation, which then goes towards the machine learning. Some literature we can use here. Of course, we always have John Ross' book. I don't mention it here, but there is some reference here on superpixels, and that you can take a look at to get more into depth of the last part of this first hour. Again, we need, as usually, some modules, just executing them. And until now, we have talked about how images are acquired, how we can improve the images and enhance relevant features, removing noise, etc. And also a little bit about understanding how the images are formed, because sometimes it can actually help you already to understand how the images were made in order to make your later conclusions. And we looked at the histogram of the images. And on top of that, we also looked at the usefulness of having a ground truth and what you can use it for to create, for example, receiver operating characteristic curves. Choosing a threshold, we saw from the histogram, that's not always so easy. If you have a, say, nice histogram, that means you have two nice bumps, and those bumps can be easily separated by putting a threshold in between them. Natural histograms rarely look like that. You have some distribution of the gray levels with peaks everywhere for different features, and that makes it harder to set a distinct threshold. This is the place. Of course, we are not always doing the perfect way work with the segmentation, so we may need to do some touch-up afterwards, and this is where we use the morphological operations. And now we are ready for the segmentation part 2, and there are different types of segmentation, and actually also the nomenclature is very confusing. Sometimes we talk about classification, sometimes of segmentation, detection, etc. But there are different kinds of segmentation. So one is object detection. Then it's more about just identifying within this frame we have what we are looking for. So here you have these tough guys standing around. You see it has identified 5 people. Another one could be that we want to say that this region is occupied by some person. Don't say who or what or anything. Just this region are human beings. Then you can go into instance segmentation, and then we can identify that we have 1 person, 2 person, 3 person, etc. And it's a little bit similar to the object detection, but this really outlines the contours of each object, in this case, a person. And problem is, when you have segmentation, want to segment something, you have to know what you're looking for. And sometimes it's not easy to find what you're looking for. For example, in this case, you probably quickly spot the fox, but you see that there are actually two Indians riding their ponies in the same image. So this is an example of how information can actually be hidden behind a lot of irrelevant information. So you see one Indian is around here, and let's see, I have actually to see. So one Indian is here, and the horse head is about here. The other Indian is here, and the horse head is here. And with this kind of images, it's very hard to actually identify anything. And that is the big challenge, to find things that have more or less the same gray levels, more or less the same contrast ratios, but maybe they have some specific shape that you're looking for. Going into a little bit more technical view of this is that you have some image features that makes our life very much harder. So usually it's something related to the measurement. And one thing is we have artifacts, not so visible now on this beamer screen, but here there are some ring artifacts. I think I also added some line artifacts. And the histogram looks something like this. It's not two distinct bumps in the histogram, but it's more stretched out, overlapping shape of the histogram. And when you try to put a single threshold on this, you see that there is a lot of misclassifications, and each misclassification is based on actually the artifacts we have. You can almost see the ring shape in the segmentation. Next one is noise. So if you have a very low signal to noise ratio, it's already by eye difficult to see these objects. And looking at the histogram, you can see that it's very widespread. These peaks at the end are just outliers of what the 8-bit can resolve. So that's just the outliers I needed to create. Otherwise, you wouldn't see anything. Then another thing that's very often happens is that you have gradients in the images. And if you go for example, for X-ray imaging, you have the classic beam hardening artifact that you get a so-called cupping, that in the middle, the image is, the slice is darker than out at the boundary. And if you try to just put a single threshold on this, you already see that the histogram looks a bit weird. Then you see that you will get a second object outside here, which doesn't really help you. And then if you add both noise and unsharpness, maybe you can't resolve the items correctly. Then one thing is you get a spread, more spread in the histogram. And the other thing is that this valley here has a higher bias, and the bias is related to the unsharpness. And if you try to segment this, you can do a pretty good job within each region, but when you come to the boundary between them, then it's getting fuzzy and you get a lot of misclassifications. You can also have inconsistent illumination. So in this case, I just added different biases. That we had a bias in intensity, and you can see the histograms here. They shift around a little bit, so there is a gliding intensity or average value of each image. That also makes it hard, because if you set the threshold, like I'm trying here, you can see that you've set the same threshold on different images. You can see in this one, oops. No, doesn't want to go. So on this one, it looks like I separated in two parts nicely. Then I get some distribution of spots, but then I go to the next one, which is a darker image. Then the threshold only takes a very small fraction up here, And what you can see is that there is probably some over segmentation here. Next one is a little bit brighter. So then we have another distribution, and you can see here, same threshold has very different effects if you have different illumination in the data. And another one is we looked at this last week already. We wanted to find different features in this cell, bone cell image. And the first task, just finding the large pieces, that was easy, but finding the smaller ones, very thin dots spread out in the image, they are much harder. One thing that we have. And also that they are very almost on the pixel level. And here we have problems with partial volume effects. Also that maybe the signal to noise ratio is ideal. And that makes it hard to segment. The other one was we have the brain cortex that we want to segment. Cortex is barely visible to the human eye. We have very tiny structures that identify that this is the boundary of the cortex. So here we really see soon that a single threshold will not do the job for us. And different filtering techniques also don't really work to help us here. So we need to find something else. We can start just trying to apply different thresholds in the image, looking at the histogram with some color coding. We can see we have the background. That's an easy one. But already the next level, you can see that due to the gradients in the image, we already start getting features around this brain, which are actually background, and so on. And you can see in general that there is some cupping in this slice. So there is a gradient making the image darker towards the middle. So this is a really hard example from real life to look at. We have several automated thresholding tools. One way, a tool that is usually a starting point people are going to is use, for example, ImageJ, interactive. It's easy to just drop the images, play around a little bit. And in ImageJ, you find a lot. You can check them out if you like. It's easily accessible. A lot of names. I'm not going to read them all for you, that you can do yourself. But these all methods, they are specifying on specific types of histograms. In some cases, you have bimodal histograms. In some cases, you have single mode, where you have a lot of tail distribution, and so on. And there are different ways. You can do histogram-based segmentation, and there are then, for example, the most used is the Otso method. And I think it was published in 1978. ISO data, intermodes, etc., etc. Then you can look at statistics and threshold the images based on that, and estimate from, for example, the entropy of the images or something similar. Or else you can go also result-based, that you can look for the method that delivers the desired result for as many images as possible. Then you can look for that you get the kind of items you want. So you know that cells are between 200 and 10,000 pixels, and the algorithm runs iteratively until it finds sufficient objects with that feature. It's a bit of a gambling, I think, but you can. There are methods that are better than this that is described here. Sometimes, when you have more specific requirements, you may have to implement your own segmentation algorithm somehow. Last resort is actually doing it manually by hand, but that's not really feasible if you have large amount of data. So looking at the histogram-based methods, in this case, the histogram of the bone cells looks like this. We have a single peak in the middle, which is essentially the background. And then we have a long tail going towards lower values, a long tail going towards higher values. And you can see here that what we're interested in are actually the low values. So the information we are looking at should be somewhere in this area. Then we have the bright edges, and they will appear in this area. The histogram-based methods, there are different ways. If you have a bimodal histogram, you draw the histogram and identify the two peaks. And between them, you take actually the value just exactly in between them. Also is a bit more advanced. It works with the statistics in the image, where you have tried to maximize the variance between the two classes, while you minimize the variance in each class. And so here you have the between variance and in-group variance, and these two give you this cost function that actually gives you a nice maximum just in between the statistical middle between the two classes. Isodata is an iterative method that starts with the initial threshold, maximum of image, and minimum of image, and then it takes the middle between them. And then it iterates until stability, that it updates the two classes, and the update is the average of each group, average of background, average of object divided by 2, and that moves the threshold a little bit in between until it stabilizes and nothing happens. In different toolboxes, we have many different implemented threshold methods. In scikit-image, there is a function called try all thresholds or something like that. And that one gives you actually a plot. Let's see if I can get this one up. Yeah, gives you the result from different types of segmentation methods. First, you have the original. Then for isodata, it tries to find something. Looks actually pretty reasonable. Lee is an interesting one. What it does, Lee and say triangle, they are quite similar in behavior. They are made for handling long tail distribution, so small classes out in the tail distribution. Basic principle is that they you have the histogram, and take the maximum of the histogram. You take either the greatest value in the image or the smallest value, and then you draw a line from the maximum peak down to the maximum value of the image. Then you've tried to find a position along the histogram that I actually have to draw it. It's easier to explain while I do that. So if you have a histogram looking like this, you have the peak value, you have the maximum value of the image, then you draw just a straight line between them. And what you do is you measure the orthogonal distance from this line to the histogram, and that goes until you find a maximum, and that is the point where we have our threshold. Lee and triangle works about this way, both of them. For those of you sitting online, you didn't see my drawing. Please remind me, and I'll send you a drawing of this, or actually I can make a picture. So, done. So, let's continue. Then there are problems with all these methods, of course. Each one has its spots which is not good, where it doesn't work. And the histogram base require a nice or a dedicated shape of the histogram, otherwise it will not work. You can do misclassifications easily with it. The image-based methods are very sensitive to noise, so you can, if the noise level changes, you will have a change in entropy, and that will then affect the stability of the method. The result-based is that it gives you what you ask for. So if you ask for objects with 200 to 1,000 pixel size, that is what you get. It doesn't care what you get, but you get that. And what you get may not be meaningful. So that's why I say it's a bit of a gambling doing this. You need some more sophisticated methods to really verify that you get what you want. There are other ways. You can also go model-based. You can try to simulate your images and include the noise, smoothing, everything. And with the simulation, you can check the stability of your images and keep track of if you identify the right things. And say that you get like more than 95% right, then it's usually pretty good results that you get. Let's see, this was a bit. You can also go and see what happens if you apply it to each, no, wait, this is kind of repeating what I said before. But at least you can do some kind of subsampling of your data set and try on a subset and see how it works. And worst case scenario, see what happens. Actually, that goes back to the again to the smoke test, or also other types that you look at what how far can you drive your method. And you need to really verify that it's doing the right segmentation. So segmentation is not worth much unless you do some kind of quality assessment on how it works. Another thing is a way to improve the segmentation quality is to use something called hysteresis thresholding. And often you have here a histogram like this. You would like to set the threshold up here to be sure that you get everything. But if you set it here, you will get a lot of misclassifications and you don't want them. So what you do is you set the threshold here, but then you get too little. And actually what you want is a combination, and this is where the hysteresis thresholding is coming in. And here you can see what happens. You have a low threshold, which gives us something that makes sense, but not all. And then you set the higher threshold, and here you have too much, but now it starts looking more like what you want to have in the regions that you identify, but all that stuff here is not relevant. And looking at the histogram, you can see that there is a tail distribution going all the way here from the object side, and you have a tail distribution going here, and this will give us a huge amount of misclassifications. So what we do is now we use, let's see if the next slide, yeah. In principle, it's the Goldilocks that you want to reduce and getting the exact right thing. The first thing is we use these two thresholds, and taking the threshold that gave us this one as a seed point, and then we let the pixels regions grow until you reach the boundary of the other ones. And as you can see here, if, for example, this one is growing, it will only reach the boundary of this one. It will not include all these because they are not in the seed. So that is a way to improve the segmentation performance. And it's a little bit of an iterative approach, but here you can see how it's combined. So we have this strict threshold, remove some small objects, some morphological cleaning, and then we have the more loose generous threshold, combining the two into this image just to see what it looks like when they overlap. And in the end, what we get is this image here. And you can see all these items here, this big one. In the strict threshold, you had a lot of missed pixels in it. Now it's completely filled. All the other things, they also look more realistic. There are some things around here which may look a bit strange. But this improves the quality quite a lot, and that's quite a used method. And that comes up is it's not always you want to use binary images. So you only have object and background, but you may have object, something in the object, and the background. So you have 3 classes, or even you can have 4 or 5 classes too. The problem is if you do a histogram thresholding, you would say essentially you have you have group 1, group 2, and group 3. If you set the thresholds like this, then you will get some kind of skin around this corner here. This white or brighter region is actually tight connected, or in tight connection to the background, but there is something happening that produces this segmentation of the middle class along the edge. And what is happening here is actually, if we look at the different cases, we have here this edge where we go from a background to the bright one. We have the case when we go from the bright to the middle one, and we have the case when we go from the background to the middle one. And if you look at the profiles, so now I just took out the one-dimensional profile from these regions that I marked up. And you can see the green one is going from class 1 to class 2. Fine, that segment's good. The orange one goes from class 3 into class 2. Also fine, that's no problem. But when you go from class 2 and class 3 to class 1, you see that you pass through class 1, class 2. Also a little while. And if this width due to smoothing in the system is more than 1 pixel, then you may get that you get a misclassified pixel when this passes from here to here. And that is the skin that we saw in the image. This can also be handled in different ways. So one would be to use also, again, hysteresis, or else you can go on looking at edge detection. So now I compute the gradient magnitude of the original image. And that gives me very strong edges, lines around the edges, and I use those as a guarded region. This region is not segmented until I want it. And what I'm doing then is to actually, again, do some kind of region growing. So I'm growing the pixels from this class into the guarded region. I grow from this class into the guarded region. And by doing that, I actually result in an image that doesn't have this effect as before. So that is also a way to handle it. And that's very often that I have used it a lot when I'm segmenting, for example, porous media samples where we have grains, grains, water, and air, for example. There should be very distinct classes, but adding the third class of water usually messes up things and makes it harder. So this is quite a good way to work with. Then we have more complicated cases, which, for example, if you have color images, then you have actually 3 channels. You also have MRI images that delivers also vector information, spectral images, and so on. So it's not only a single value in each pixel, but you can have multiple. And one thing is we can look at feature vectors. We have each position correspond to some kind of information vector. In this case, we can look at an improvement of images. This image you can see here, there is a gradient in it, and we want to remove this gradient. And to improve that, we actually compute an image that corresponds to the background and subtract it from the image. And the operation we do is a median to remove some noise minus a very wide Gaussian filter. So here we have the kernel size or kernel radius is 20 pixels. And by that, we smooth out the image very much. And that gives us this background that we wanted to have. And from that, we can get much easier information to segment. Another one is that we have some kind of feature table in this. So we have on one side, we have the positions, we have an intensity, and we have another vector here, which is text. So we have the image labeled already. That says true, 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 true. And so all of these pixels apparently are in the text. And here's a false, so it's outside, just the paper, and so on. So this is a table that we are going to work with now in this training. And if we look at the different features, we have a histogram distributed over where we can see that the text is distributed like this, and text false is distributed like this, and text true is distributed like this. Very strongly overlapping, so it's not easy to put a threshold here. This is, by the way, a logarithmic scale. To do something with the image to improve the segmentation quality. The ROC curve, just to compare, looks, well, somewhat good. You can see that the true rate, but soon we are going to quite many false positives. But it's a good starting point. And now we want to add more information. So based on the image itself, we want to add something. One would be to add some edge information. So here we have the difference of 2 Gaussians. We have Gaussian kernel 1 and 2, and they have different widths. And what you can see here is that when we subtract them, we get these curves, the green one. So that is the filter kernel, and that's more or less an edge detection. And then we need to, let's just see, that's, oh, I didn't split that into different. Okay. So now we add another feature to this segmentation, and that is edges. And then we can see how they are distributed. So this is the original, and this is the difference of Gaussians enhancement. Already looks also better than the one before. the original actually. And what does this look like when we run the histograms? Now you can see that things have shifted a lot. So now you have a very big distribution of pixels in text are true, and the remaining are in text are false. And the contribution here is also much less. So if we want to look at the performance using the ROC curve on this one, you can already see that this kind of feature vector is more likely to perform better. So you can see that we actually raised in the beginning here from 0.2 to 0.6, and before it starts producing false positives. And that is already a good result, and area under curve is also increasing somewhat. So I already hinted why the filter perform better, and you can see that the distribution is in this way, that you have the histograms are much more overlapping in the first case than in the second case. And with that, we also have a better segmentation performance. So you can even see if you put the threshold somewhere between here, you have this 0.2 positive true. True positive. And if you put it over here, you have about the 0.6 true positive. If you want more, then of course you start adding more and more from the non-text items, and then the performance is degrading. The next thing is a kind of unsupervised classification or clustering, and it's a very popular method to work with, and it also works very fine with multi-dimensional data. I did it with some spectral images and got very nice results actually. So each pixel had 1,000, I think 1,000 values, and still with the help of that, it could actually find very good segmentations. It's also a quite fast method, and let's see how it works. We have now some example data. We have measurements in X and we have measurements in Y. And this data, you can see there is one blob here, one blob here. If you would be critical, you would possibly say that there is actually two blobs here. So there is some separation between those. So let's take a look at that. Yeah. In this case, we say we have two clusters, and this is what it gives us. If you're running this k-means segmentation, so that is a clustering method. And this method has also kind of the drawback. If you ask for two classes, you will get two classes. If you ask for 10 classes, you will also get 10 classes. Make sense? Who cares? Not this algorithm, at least. But anyway, what it does now, it nicely finds that we have one class here and one class here. And the basic algorithm is working in a way that first you have your unclassified data, and on the other side, you want to have your segmented image. And in the initial case, the segmented image is randomly initialized. So that means every pixel gets a random class out of the ones you have decided. Then, based on that, the algorithm computes the average in class 1, 2, 3, etc., and does an update of the classes based on this segmentation. And then it iterates until there is no changes anymore. And then you have your classes. And that it really goes fast. In 2, 3, maximum 10 iterations, you already have your segmentation. So it's trying to minimize more or less the standard deviation within each class. So here you can see what happens when you start increasing the number of classes. As I said, this one we saw already, if you have 3 groups, it actually finds one group here and one group here. And in the iterations, what it does is it computes the mean around this class, mean around this class, and then the ones that are closest goes into that class. Here it gets actually 3 mean points, and the data points that are closest to this one are assigned to this one, and so on. Now, if you start increasing the number of clusters, then you see that it starts doing some kind of over segmentation, that it starts splitting into more groups, but visually they don't even make sense. So here it doesn't make sense to go further up to a higher number of classes. So then is the question, what kind of vector spaces do we have? We have already looked at maybe using different kind of filter kernels. I mentioned we can have spectra. Can also be that we have locations that we associate with the data, and could be orientation, shapes, a lot of things, and depends on what you want to classify using this segmentation. Sometimes you actually do image segmentation, and sometimes you use k-means to do classifications in data that you already measured from images. I think next week we are going to look at object features. So that could be the shape, there could be the area, could be position, and things like that. And that could also be feature vectors that you want to plug into a k-means segmentation clustering. So let's try to add some spatial information to k-means. In this case, we try with a cortex image, and here we add the x-coordinates, the y-coordinates, some weighted neighborhood. So I think that is it a box filter or is it Gaussian? Okay, so there is some blurring, we have some edges, horizontal and vertical, and then we can try to add more of this information into the clustering. And here we start with just the intensity and see what k-means does, and intensity and positions. And the first thing is the segmentation out of that is you get the quadrants. The reason is that you have way too, let's go for that, way too strong weight on the position compared to the intensity values, and that is why it didn't work. So if we instead would divide the position by a factor 10, then you come in the same order of magnitude as you had on the other values, then it starts making more sense. Still has some tendency of giving 2 sides here, as up and down, but now we at least get this frame here segmented. Still not a good segmentation, but it gets a little bit closer. So just to give an idea how you can add more information into the image. So when we can use it, so for example, you can use it on single images, like now the cortex example. You can use it on bimodal data. So if you have 2 modalities, I always talk about X-rays and neutrons, but it could be something else, X-rays and MRI or ultrasound or something. And it can also be hyperspectral data. So you have a spectrum at each point, and then you can use the clustering on that. Today I'm talking a lot. Let's make a break here, and then we continue after the break.